Hello folks, this is Mark. I haven't created any new content in a while, but I hope to change that starting today. Relatively speaking, there have been a lot of things happening in the world of EPANet in the last 5 or 6 years. The thing I want to talk about today though is EPANet version 2.2. This version was released in July of 2020. I don't know Lou Rossman, formerly from the EPA personally, but from my view, from the sidelines, it seems like Lou's last years at the EPA were spent further developing EPA SWIM, and not as much time was put into furthering EPANet. I believe the last release prior to EPANet 2.2 was back in 2012. It seems that since the last release, though, folks in the industry, including Lou after retirement, and other folks in commercial and academic interests have been itching to take EPANet development further. I have that same desire and interest. At some point, the Open Water Analytics group formed and took EPANet engine development the open source code route. Also, in around 2015, the EPA decided to spend some money to upgrade EPANet and EPA SWIM user interface. That effort seems to have fizzled out in the last couple of years though, but I'll cover that in another video. This video will be a quick look at what's new in EPANet 2.2 and some general thoughts on the release. Okay, first, and not insignificantly, they finally have been able to put scroll wheel support. As you can see, I'm not clicking on the zoom and whatnot buttons up here. I don't know if you can hear my little scroll wheel in the background, but it's zooming in and out quite nicely. So that is a great improvement for usability's sake. Another fix that seems to have happened, I don't know if it's just machine dependent, but sometimes when I open EPANet, the toolbar button icons kind of disappear until you kind of float the cursor over the top and then they show back up. I haven't, in version 2.2, I haven't had that problem, but also I use this on multiple EPANet on multiple machines with slightly different specs, so it could be a machine dependent thing. Another feature that they've added in tanks is the ability to overflow a tank and capture that total volume. So here's in the tank property window, a yes or a no for overflow. And what that reports is not a total volume per se, but a spillage rate. So you could then do a summation of all time periods if you needed the volume. Okay, also some new hydraulic options that are actually pretty cool. I was a little skeptical at first until I kind of dug into them and tested them, and they're a worthy addition, and I believe they've worked really hard to get these in here. First one, first category. Is max head error, max flow change. So these are additional convergence criteria in addition to the accuracy parameter. The accuracy parameter is how old the EPANet 2 decided if it was each iteration was solved sufficiently. The sparse matrix solution was sufficiently converged to move on to the next time step. And what that meant was the sum of all the flow changes between iterations divided by the total, or the sum of all the flows in the whole network. That had to be less than a certain threshold, usually 0.001, which would be like 0.1% change. But the problem that has is, in my experience, sometimes around PRV, pressure reducing valve, or PSV, pressure sustaining valves, and there may be other instances, but the continuity error around certain types of valves can be alarmingly high. And I believe they've put these additional criteria in here as a way to kind of reduce the jumping around of the numerical results around these types of nodes, links in EPANet, such as valves that tend to bounce around because of the status checking in the EPANet engine. So you can, for example, if your units are ES units, so feet, CFS, etc., you can put a max head error. I typically found that 1 foot of head error, max change between iterations, was somewhat suitable in my testing. As far as a max flow change, that's in my instance, I usually use gallons per minute GPM. And I do have some testing results here. And it's always a balance between and adding solve criteria, convergence criteria. It's always a balance between time and accuracy. And might as well just go ahead and show some of these results. I did a model that I use at work. I put the duration as 400 hours. I solved it with the older version of EPANet 2.0, which is so the baseline for this and some other testing is just under a minute. When I bumped the flow criteria, or added in the flow criteria, there was a significant time increase. Head criteria, there was also a time increase. But I also have in here the pressure dependent analysis as well, which I'll talk about next. So traditional EPANet 2.0 demand dependent analysis means that no matter whatever demand you put in the model, it will extract out of there, even if the residual pressure is ridiculous and unachievable, like negative, whatever the case may be, negative 100 psi, negative 100 meters. It just sucks the water out of the network, even if the residual pressure is not actually achievable. The alternative that they've added in is a pressure dependent analysis, meaning that you can set some criteria to limit that behavior. So, for example, you can say below this minimum pressure, the demand I've entered actually goes to 0, and therefore helps eliminate the behavior where you could go below a theoretical maximum or a minimum pressure, meaning vapor pressure. So I'll show that in my testing in a minute. Okay, so here's how this works on the pressure dependent analysis. So for just the example purposes, I am showing a normal demand of 100. This could be GPM, this could be cubic meters per second, whatever the case may be. We're just using unitless. Again, pressure unitless because it kind of doesn't matter in the formula. I'm showing a minimum pressure. That's the pressure below which the demand would go to zero. The required pressure is the minimum pressure you need to get the full 100 amount of demand coming out of the model. The exponent is just a way to shape the curve between the zero and the full. That puts a shape. So you can see here that I've also started out here with 100 psi or 100 units of pressure down to my minimum, and you can see kind of what the shape of that turns out to be. I can change the default is 0.5. That kind of gives a more rounded shape to that. You can change the required pressure and so forth. I actually had to do a little research on here to decide what in my networks that I analyze, what would I use. So I'm just going to kind of quickly go through that. I looked at some here in the United States. A lot of people have outdoor landscaping. They have irrigation components here on this Hunter website. Maybe the type's kind of small, but it talks about the minimum pressure to make these function is 15 psi. Also, some criteria for indoor plumbing is this website talks about 30 psi being too low. Usually the municipalities and utilities that I'm used to and the state water quality boards say that under emergency circumstances, you get at every connection you've got to maintain 20 psi or more. The criteria we use in our utility is state mandated 35 psi, but we shoot for at least 40 psi everywhere in our network. So it's kind of something you have to think through. So in our network, if our absolute minimum that we have to maintain is 35, you could say that people are used to the pressure of 35. So that's the number I chose as the required pressure to get the full demand. I also rationalized that houses in our area don't have basements. They're kind of slab on grade. So usually there's a little bit of elevation rise from the meter to the first floor elevation. So I kind of put 5 psi as a minimum operating pressure to the lowest elevation device. So roughly, 5 psi equivalent in feet, maybe 10 or 12 feet above the meter. And in water modeling, of course, most people consider ground elevation as what we model for pressure. So that's roughly where our meters sit, is just a little bit below ground elevation. Okay, so why did I choose this pressure, the exponent is 0.8. I guess I figure that in this, once it drops kind of below our 35-ish pressure level, people aren't used to that. Devices aren't really set up for that. So I think the demand would drop quite rapidly down here to 0 at 5 psi. Okay. And I hope to do a more in-depth, detailed videos on each of these in the future. So the actual equation there for what the effective demand is in the model would be the full times the ratio of these minimum numbers, and then multiply that factor by the exponent you choose. So when is this actually useful? Because as I'll go back to the results here in a moment, it does add simulation time. So previously I've been tasked with designing irrigation networks for farming, as well as for like a city park. I believe we used emitters type features and junctions for that, which gives a different not demand, but a different flow leaving the network from each emitter depending on pressure. Also, emergency situations. Here in Texas, February 2020, we had a disastrous cold weather event that gave us outages everywhere, lots of main breaks, had trouble keeping water in the network. So a dewatering scenario kind of makes a simulation more realistic when you start simulating main breaks everywhere and water not available in all areas. It would be helpful for that situation as well. So I think overall it's generally a good feature, a good idea. Maybe not for all analyses because it does extend the simulation time. Going back to my results over here, the baseline again was EPANet 2.0. These are all the same networks run for 40 hours duration. And also note that maybe just the EPANet 2.2 engine, for some reason, is maybe 20% slower than the 2.0 engine. And that's kind of surprising considering some of the advances in the engine that they're showing in the release notes. Anyway, so the baseline again was a little under a minute with EPANet 2.0, simulating the same thing exactly in 2.2, little 1 minute 20 approximately. Then adding on kind of a minimal, or adding on the pressure dependent analysis. That's like a 42% above baseline. So that's not insignificant. So you kind of want to decide if that's worth adding in that extra criteria. Down below here, again, I showed this earlier. This was the pressure dependent analysis plus some of the additional criteria. We can see that if we have pretty strict convergence criteria, like 0.1 flow units, it can really get up there depending on what thresholds you set for the convergence criteria, and that's on top of the pressure dependent overhead because in the pressure dependent one, you're having to recalculate all of the demands every time step, every hydraulic time step that the model model solves. So it can get up there. If you just really need it to be accurate, and these are the convergence criteria and the pressure dependent analysis is critical to your situation, well, then that's what it's going to be. Just have to live with it and enjoy the benefits of all the hard work that they put in to add those features. So some performance enhancements they're listing in their release notes. This first one they don't list, but it's something that I requested, I don't know, back in 2017. I think my request got lost, and somebody else I noticed on GitHub had posted it as well in 2019. Looks like they were able to understand what the problem was and solve it. I'll hopefully cover that in a future video, like what that issue is. But basically, if you are kind of starting out an analysis, don't know what the pump station or pump specs would be, you can just put in constant power, constant kilowatts, or constant horsepower as kind of a placeholder to kind of see what kind of power range you need for a pump station. If you do set some simple controls on that, though, when you close a constant power pump and then reopen it with a control, the flow doesn't come back up immediately in EPANet 2.0. So supposedly they've fixed that. They describe kind of how they did the fix, and I believe it is that they reset when the pump control turns it back on. They reset it to the initial time step in a simulation, which for all links is set to 1 CFS, so that they do that as a starting point, and then let it iterate from there, and it'll converge on the right flow rate. They also talk about an updated hash table algorithm with this multiple minimum degree. Mainly this helps for just a steady state or a single period simulation, because during your simulation, this reordering or the hash table reordering and the purpose of that is to get your solution matrix to it becomes a sparse, it is a sparse matrix, but they try to get the coefficients as close to the diagonal as possible, because that's a more efficient solution, I guess, in the numerical engine when you're solving sparse matrices. So once that's reordered, it doesn't have to be done again, so that as your duration on your extended period simulation goes longer and longer, then the percent increase in speed diminishes, because as a percent of the total simulation time, the reordering is less and less. Also, fixed a memory leak when saving output. I don't know that I've ever experienced any issues with that that I can remember, but some people must have seen that problem, and I'm glad they found that and fixed that, because memory leak issues are kind of hard to troubleshoot. Also improved handling of near zero flows, and if you've ever been using EPANet and the flow should be zero, yet when you graph it over an extended period, it shows the graph bounce. I don't have one of those open right now, but it shows the graph bouncing around when it should be more smooth. I think that's more of kind of annoyance than anything, but that's kind of cool that they worked on that too. Also, improved water quality mass balance. In the text report of the simulation results, near the end, they kind of show this, if you do a water quality run, kind of some mass balance statistics. So that's pretty cool. I don't know that I've ever even thought about that, but I'll have to dig into that in a later video. Also, if you like to tinker with EPANet, they've enhanced the toolkit. So there's more functions that are callable. Engines run in a thread-safe manner. I can't really speak to that very much. I believe that just means that you can call the same code from more, if you're running multiple simulations at once, it doesn't cause problems or crash. You can theoretically build the network from scratch, whereas the toolkit for EPANet 2.0, there's no adding or modifying or deleting of features to a network. You have to digitize it or import it from some other software. But here in the toolkit, you can actually just read that information from a source like GIS or CAD or spreadsheets or whatever, and add those features one by one into the network before you then move on to probably simulation. So that's pretty cool. Just wanted to shout out to the collaborators putting the work into the open water analytics to push this along further. Of course, Lou Rossman, I believe he's still retired, but still contributing. So I think that's really awesome. And I know a few of these people, but most of them I don't. Just wanted to make sure they got credit for all their hard work. Anyway, now just some general thoughts. It would have been nice to see some enhancement of the background stuff. Let's see. In EPANet, there's some background stuff you can backdrop, they call it, but that's limited to a bitmap, which gets kind of clunky because you're limited to roughly half a gigabyte, and a half a gigabyte for a bitmap just does not cover a very large area in high enough resolution. You can also use a Windows enhanced metafile, which isn't really much better from my experience. So, but I think that was kind of the point of the new interface that the EPA was working on and paying for, that kind of has stumbled along for 5 or 6 years, and I think they've kind of given up on it. They were building that with the building blocks of QGIS, and the word I got from EPA was that it just doesn't work very well for large models. So I think it's kind of odd that they would just give up, but so be it. I'm working on a QGIS extension plugin to run EPANet and other things. So hopefully that'll be coming in the future. Anyway, I like the scroll wheel support. That's really handy. It's kind of a pain in the past to use these plus minus buttons. The new pressure dependent demand feature is pretty cool. It seems to have useful applications. But for kind of a typical planning type simulation, maybe not so much. It just kind of slows down the simulation. I like the new hydraulic convergence criteria. It may be helpful in more complex models with lots of PRVs, PSVs, which I've built before, and seen this convergence problems around, or continuity problems around certain PRVs, PSVs, etc. I don't really have a big opinion on the other features since they don't, the other enhancements, since they don't affect my daily work. Overall, I think it's a great release, positive step forward. So anyway, please look for more videos in the near future where I take a deeper dive into using these new features. I'll also be making a separate video on the convergence criteria and deeper dive into that. But for now, thanks for watching. Please hit like and subscribe to help others find this video if you thought it was useful.